Linear algebra and linear operator theory is very fun. All right, so here's the definition of homeomorphism, homeomorphic, topologically equivalent. They're all kind of thrown around interchangeably. So I have X and Y are topological spaces. And F going from X to Y is a bijection with inverse, F inverse going from Y to X. If F and F inverse are continuous functions, F is called a homeomorphism. Y, F inverse goes from Y to X. So so the picture you should have in your head is this. F goes from here to here. And F inverse goes from here to here.
Okay. Thank you.
And if you think about all the things that you've learned so far, like if you're in abstract algebra, isomorphisms, the first criteria of an isomorphism is it has to be one-to-one and onto. And then it preserves group structure. You also learn these kind of things in analysis, but kind of not. I think you want to preserve limits. We call that isometric or isonorm. You do learn it. I'm trying to think in linear algebra if you do have one in linear algebra. It's just they teach you matrices first, and then they teach you linear transformations next. And then they have this big theorem. There should have been a drum roll right there, but it might not have been because it's towards the end of the semester where they connect the two and say there's a one-to-one and onto map from the world of matrices to the world of linear transformations. And that is really awesome. That is really awesome. But I remember taking linear algebra and not feeling that. I don't think that they explained why that was so important. I really think they should go the other way around. Teach linear transformations first. The beauty of it that it actually can scale things and change things and rotate things, all the things about linear transformations. And then say, by the way, we have a map that takes you to matrices, and matrices are easy to work with. And I think everybody will appreciate that a lot more. I don't know, maybe I'm wrong. Question?
Man, I thought when I was thinking linear algebra, it felt like it was a lot more geared towards like the A's, B's majors and like all of that. Like all the people were using like more linear linear optimization and stuff like that. It was more about coding, and we lost a lot of there's very little proof writing.
I don't know if you should do a lot of proofs in there, but you know, the reason why something's because Colonel Clark and I really feel like we should teach your stat classes with linear algebra, because really you're working with covariance matrices, you're talking about linear algebra. So it's a big deal.
That's why 376 is just like piecing those up, just like.
But that's what 376 is about, right? You can just become a good R coder.
Yeah.
Yeah.
Yeah,
I liked it. 476 is that class if you want that class.
Oh,
476 is a great class.
Only 18.
I got 20. Yeah.
Below 20 until next semester. My first semester ever.
Who told you to take a double major? That's what I told my son.
That was a chance.
It was a choice.
And so I'm not gonna take the class that I've already got prereq for, or that I've already like co-rec. This 376 and 476 like count for the same thing later on. So it's like.
476 is an awesome class.
I'm sure it is. I just can't justify it on my ATAP. Like, hey, sir, or I'm talking to my dad, like, hey, sir, why don't I just take basically same class but more? I mean, I'm taking 376. I'm in the rest already.
No one had that exact conversation at last. Different answers.
So I asked Chaos and Fractals this question last time because the way Devaney built up, like Devaney kind of like stuck in the advanced calculus, the real analysis and the topology you needed as he went along. Sometimes it's like you read the proof and go, whoa, he's using Bolzano, wire stress and all kinds of stuff and he didn't say anything. But he came to definition of homeomorphism and I asked the Chaos and Fractals group, if you have a function that's continuous and it's one-to-one and onto, then it has an inverse. Won't the inverse be continuous already? Like, why do I need to add that condition? And we didn't prove it in that class, but I kept thinking like, hey, I don't think I need that F inverse is continuous. So here we are again. Why do I need F inverse to be continuous? Don't I have it already? If like F is really nice and well behaved, it's continuous. I know the inverse sets maps to inverse sets, open sets here. I know that it's one-to-one and onto, so I know that every dot here has a corresponding dot here. So I know all those things. So why do I really need F inverse to be specified to be continuous? And I'll let you think about that because everything I could think about, F inverse was continuous. Almost everything I could, not almost, like everything I naturally could think about. So I started out with, I actually should have made you guys go through this, but I started out with just finite topologies, like just a couple sets. And I tried to force F inverse not to be continuous. Couldn't do it because what happens if you take a TX, let's say A, B, an AB, something like that, and a TY, well, the one-to-oneness means that if I have four things here, I'm going to have four things here. And all the open sets will be those four things here. And then when you invert them, they're going to go back to the original thing because it's one-to-one and onto. So everything corresponds down to, let's suppose I have these four things here. They're just going to map down to one by one to each one of these things here. So I could not get a counterexample with a finite number of sets. So then I thought, okay, maybe there's something in the reals to reals. And I get a homeomorphism and could I come up with a counterexample there? Try as I could not come up with a counterexample there. So here's my strategy. This is why I say that this class is hard to prep unless you just blow past all this, but I can't. I had to stop myself and just ask these questions like, so this is what I was doing. For F inverse to be continuous, it means that its inverse has to map open sets to open sets. So that means if I have an open set here, U, that set has to be mapped to an open set here for every open set. That's a definition of continuity. So I kind of boil it down to like, I have to find a counterexample where I have all these other properties, but my F can't map an open set to an open set. And I spent some time spinning wheels on it. So this is my spinning wheels. Okay, so I finally came up with a counterexample. So the first thing I realized is it can't be finite, because if it's finite, there's no way I can build a counterexample. The second thing I realized is the question I asked Liz last semester, what if it's just R to R? Absolutely true. If I have F is continuous, F is one-to-one, F is onto, then the inverse is continuous. So I can't make up something on my usual topology where I can see things and understand them. So then, because I needed infinite sets, I thought, let me take the easiest infinite topologies I know. Let me take something where X is the usual topology. What's my favorite topology? That's infinite. finite complement topology. So this is why I say that Dr. Sargent is really good to go. Like we were just chatting in the office and he's like, finite complement topology is a counterexample for everything. He'll be able to answer your questions off the bat. If you admire Dr. Clark, Dr. Sargent's like, I think the best pure mathematician that's walked into our halls for the time I've been here.
Where are you going to be next?
Washington, DC on Monday, Tuesday, and Wednesday, and then come back and teach foundations Thursday and leave to Dallas that day. So my F is going to go from R to R because that's the topological spaces. They just have different topologies. So the X is R on the usual topology and the Y is R under the finite complement topology. And I'm just going to let F of X be X. So F is a bijection. It's actually, I'll use one of John's words, obviously. Obviously, this is a bijection. The second he puts that down, though, on his homework, I put, why? No, by the time you have your PhD, enough people have poked at that on your homework that you don't say it anymore. F is continuous. So let's see why F is continuous.
Can say it, why can't I? Exercise to a little bit of algebra.
Textbooks say it because they don't want to type it.
Yeah, same. I don't want to write it with my hand.
The only percentage on no, but that's a 1-1 function. That's just convenient. Not knowing you're not going to write it.
But I don't know.
So is F continuous? Yeah. So if I take an open set in the range, it's going to look like this. Or actually, I kind of wrote it the way Michael writes it. So it's easier to think of it like this. You write it like that all the time. So if I take F inverse of V, I just get V, which is open because it's the union of basis elements. Right. So I'll put that on the next slide, but V, F inverse is just X again, right? F inverse of X is X. And V is a union of open sets, which is open in the Euclidean topology. So this is open, the inverse is open in X.
John. This is because F of X is X, right?
Yeah, I'm using F of X as X.
Yeah, it's because
I actually didn't want to go to infinite sets. I was like, I should be able to come up with something. And then I finally realized, well, it's really hard to come up with a counterexample when the statement's true. So I had to find something infinite, and I wanted to keep things as easy as possible still. So F of X equals X seems easy. All right, so, but if this is because V is the union of basis elements. But f of u for u open in X is not open in the finite complement topology. And these were the first homeworks I gave you. Just take an open interval. You're done for. You remember me giving you those problems or you just, is this open? Is this, yeah, so.
After here, you're saying you can't go both ways.
Yeah, so this was, so
Um,
remember, like I was reducing down to coming up with this counterexample by thinking, okay, what does it mean for F inverse to be continuous? It means that its inverse, which is F, would have to map an open set to an open set. Right? So that's the definition of continuity. So I'm really thinking about taking an open set in the X space and mapping it to something that's not an open set in the Y space. Because remember, in the finite complement topology, the open sets are the ones where the complement is finite and the complement of U is not finite. Okay, so now I believe it. You need the condition F inverse is continuous. Yeah, but I don't, I think I'm still right. I know I'm right because I actually proved it. You don't need the condition F inverse is continuous from R to R in the usual topology. Why? You can actually see why, right? If you have a union of open intervals, you pull it out of the function, that's foundations math, and it still stays open.
So for that. Is the only difference between the injection. Like simulation of the inverse.
Are continuous. So if you think about topology, what do we want to preserve if we have two planets? Like these are two planets. I want to say they're the same, right? And all of this, what did you have so far? Just a foundations type course?
Yeah, I think it was like foundations.
Okay, so in everything that we use, like any like if you take abstract algebra, they start out with something called groups. And then eventually they get to a question, when are two groups going to be the same? Right, and so they need a function that's one-to-one and onto that preserves group structure, and that's called isomorphism. Here, we're in topology, and we have two topologies, and we kind of want to say they're the same. And so, let's see. Everybody knows I'm teaching right now.
It's on there.
So here, like I gave you an example of why we want that. So some things are easy to prove here, but they're not easy to prove here. And the example was this, to show this is chaotic. It's hard. This is on the usual topology. So we did a lot of math on some other weird topology. And then it turns out that those two were homeomorphic to each other. And so like, because that map was chaotic in this easier topology, it's also chaotic here. So that's why we do it. So one-to-one and onto are not the same. We need to also add in continuity and inverse being continuous to force this topologically equivalent space.
Okay, that makes sense.
So if I have, so we would say if I have a homeomorphism between two planets, then those two planets are topologically equivalent. That means anything I prove on the first planet is also going to go through to the second planet. And this is how you get to the coffee cup and the donut being the same thing. There's a homeomorphism between the two. So they're identical.
Both the same thing where it's like a circle and squares.
I don't think,
Or would you say in front of just like unit ball and unit cube?
no, I don't think you can say those things. A square and a circle won't be the same thing because you have sharp corners on the square.
Yes, that's not.
And you can't say that.
Yeah, Jack just keeps dropping his words, like people know it's.
Obviously, clearly.
I mean, all I know about metaphors is that they're locally splitting.
Manifolds are just subspaces. So you can, like from vector spaces.
Of course, the man can't.
I have another example that he had in the book. I'm gonna skip it actually. Let me see where I'm at. I'm gonna skip that example. Did I give you some, another in-class assignment problem on? Okay, I'm gonna skip that, but I do recommend you look at it. He has an example a little bit later on. Feels a little, maybe I will go over it because this will make chaos and fractals students feel good.
Let's get the knots.
You can do chaos and fractals on top of knots. I'll show you, at the end, I'll show you a really cool problem.
I know nothing about chaos.
We can be proved because we put in finite digital bags. That means integers now.
It's not it's not
Okay,
homeomorphic.
make sure I was on the same page. I guess I didn't think of that.
And it's only